This is a Lowell Observatory podcast.
5, 4, 3, 2, 1, 0.
Welcome to Star Stuff, a space oddity.
Hello and welcome to the latest episode of Star Stuff Podcast. My name is Kevin Schindler and I'm the historian and public information officer at Lowell Observatory. And I'm joined today by Apollo 9 astronaut Rusty Schweickart and Dr. Kyler Keene, one of the astronomers and head of technology here at Lowell Observatory. So for the next 35 minutes or so, we're going to talk to astronaut Schweickart about his time as an astronaut and some of his time in Flagstaff here and learning geology and stuff like that. But then we're going to get into some really exciting stuff with his B612 Foundation and looking at asteroids, their threats and such. And we might even have a couple cameo appearances by Rusty's sons. So I think we're going to have a good time. Thanks, both of you, for joining us. Mm-hmm. And thanks for coming back to Flagstaff. You were here years ago.
Yeah, and several times since.
Yes, yeah. Right. So we want to get just a little bit of a general idea of some of your early days, but then we're going to really focus on the B612 and such, because that's really exciting work you're doing. And it ties in with astronomy going on here at Lowell Observatory. So you were from a small farm in New Jersey.
Right.
How do you go from a small farm in New Jersey to up in space?
Well, I got interested in astronomy being on that farm because the skies were really crystal clear at night. We had very little light pollution, so the stars were always interesting to me. And we had an Army base, 20 miles north of our farm. And during World War II, they were shooting radar at the moon, and they were having it, for whatever reason, following a searchlight that went through the sky. So I used to lay there on my bed watching them bounce radar off the moon, and I got very interested in that kind of thing. So from there, being kind of technically oriented, I guess, by nature or whatever, ended up very interested in chemistry at first. We had the Chemcraft chemical set, right?
Oh, yeah. Mm-hmm.
And I used to build my own, bombs and things as a kid. And so I ended up applying to MIT, got into MIT on a scholarship, and spent about 2 months learning that chemistry was not for me. And so I went to my second love, which was airplanes and aeronautical engineering. So that was the way I ended up, graduated, became a pilot and all of that. And,
Sure.
As a pilot, two things you want to do. You want to go faster and you want to go higher. That leads only one place, space. So,
Did you apply for the first when they first came up with the astronaut program, or a little?
No,
bit later?
I was in the Air Force.
Yeah.
I can still remember I was playing pool one night when I heard on the radio that the first selection of astronauts, the so-called original 7, were selected, and then the second group was selected about a year later, and by that time I was actively interested in becoming one, and ended up being lucky enough to be able to meet the criteria and apply.
Yeah.
Made it.
Do you have a specific idea or goal for what you would want to do when you join the astronaut corps, or is it just whatever they told you to do?
No, it's what fly in space. I mean, whatever came up. Obviously, everybody in those days, everybody once President Kennedy had made that commitment of the nation to sending someone to the moon and bringing them back by the end of the decade. Everybody wanted to, do that and be that person, but. Unfortunately, I was the first one to fly the lunar module, but I never got to run around on the moon, unfortunately.
Yeah. But did that ever bother you? Did you really want to do that? Or, your mission was so important for the success of the whole program.
Yeah. Well, you are a team, and it's obvious everybody's not going to be able to do it. So being the first to fly the lunar module was good enough. I obviously would like to have flown, onto the moon, but then I ended up going on Skylab and, other things. But we can talk about all of that later.
So part of your preparation while while NASA and the astronauts are trying to figure out how to ride rockets that don't blow up and get into space, you also did geology training.
Yeah. Yeah.
So that when those astronauts who went to the moon, they would kind of know what to pick up and could describe in mission control and such. So what do you recall from coming, because a lot of that was done here in northern Arizona, at Grand Canyon, Meteor Crater, Sunset Crater.
Yeah.
What do you recall of that training?
Well, I mean, we went to a lot of the most fascinating places on Earth. I mean, where you have volcanoes and things of that kind, all sorts of geologic features. I mean, it's hard for people to really remember today, but at that time, we didn't know whether the craters on the moon were impact features or whether they were volcanic. And everybody was pretty familiar with volcanic, so I think there was even a bias that that's probably what they were at that time.
Yeah.
That's a little hard to imagine now because every little kid knows that the moon is full of impact craters. But so we studied both volcanism and volcanics and impact features, and of course, if you want an impact feature, there's nothing like going down to Winslow and hiking out to the Meteor Crater. So that was probably, I would say, the most memorable thing in this area. I mean, Meteor Crater is really so special that there just are no other features around that are that dramatic. Partly the fact that it's in a desert area, so it's not obscured by trees and a lot of weather, at least in the recent geologic history. It's pretty dry and well preserved.
So now you didn't walk on the moon, but still you orbited Earth, and a lot of what you learned in geology was aerial maps and stuff like that.
Right.
Even though you didn't walk on the moon, what was the impact of that training you did in northern Arizona on your mission?
Well, the most direct thing for me, as a matter of fact, I was just thinking, because I think I told someone about this yesterday, but the photo lab at MIT, at Johnson Space Center in Houston, one of the guys there, a guy named Herb Tiedemann, was one of the top-notch photographic experts there who trained us and did a lot of things. We had, Hasselblad cameras, the best cameras and all. And Herb did a lot of writing for Arizona Highways magazine. And so Herb kind of pulled me aside at one point before the mission and said, "Hey, Rusty, I really want you to be able to get a picture, from space of the Grand Canyon. I've made a contract with Arizona Highways. I'm going to write this article, and I'd really like a picture of the Grand Canyon." So I said, "Okay, Herb, let me know when I should be ready for it, and when our track is going to take us directly over, et cetera, et cetera." So the time came, and I'm going over to the window and getting the Hasselblad ready and looking out the window and looking down, waiting for the Grand Canyon. And I'm looking at the clock, and the seconds are ticking down, 10, 9, 8. And I'm thinking, I don't see the Grand Canyon. How can you not see the Grand Canyon, right? But the fact of the matter, the truth of the matter, was I pointed at the camera and I clicked the shutter, plus 5 seconds, minus 5 seconds. I thought, I hope I got it. I really never saw the Grand Canyon. At least I never recognized what I saw as the Grand Canyon. And I came down after the flight, and Herb came walking over to me one day shortly after we got back, and I thought, uh-oh, here comes the bad news. and Herb was just congratulatory. It was wonderful. I got a perfect picture of the Grand Canyon, And I said, "Really?" And he said, "Yeah." And I told him that I'd never really seen it. And you don't get that third dimension when you're, especially if it's near noonish, you don't have a lot of shadows and things. So I really did not see the Grand Canyon when I took the picture of it, but it got published in Arizona Highways.
But you knew you were even though you didn't see it, you knew you were in the right area. So you still captured it. So
let me say, Herb knew that our track was going over in the right place.
Well, you got it. So that was the important.
Right. That was the important thing.
Were there other aspects of the training that were relevant too? I imagine if you're, even if you're doing the geology, if you're in the spacesuit, that helps when you're, out in space, knowing how to manipulate it, move around, especially if you're doing something like an EVA. That's relevant for that training's relevant too.
Yeah, well, the EVA training is certainly very relevant, and most of the EVA training that we did, and I led a lot of that, was underwater, where you get yourself neutrally buoyant, and of course you're never perfectly neutrally buoyant, and if you think about it, even though if you take an astronaut in a suit underwater and you turn him upside down or any way, and he doesn't really move, if you put him head down, in the suit, he doesn't fall to the bottom of the tank, all well and good, but the guy inside is still, the blood is still rushing to his head, and you're being pressed into the upper part of the suit, So we would often come out of the training in the water tank like that with, bloody stripes on our arms and things like that from moving around in the water. So you're grossly neutrally buoyant, but inside the suit, you're still in gravity.
Yeah.
So when you get into space, frankly, it's much easier. I mean, everything is very comfortable. You're literally floating inside a floating suit, and that's the right way to wear that suit. You wear it on the ground, and it's really cumbersome and heavy.
And you for the first time used the Apollo spacesuit.
Yeah.
The one before that, the Gemini, was notoriously horrid.
Horrible suit. Yeah, I mean, I don't want to badmouth. It was one of the first.
Yeah.
It was the first spacesuit people really wore and tried to go EVA. But what you want to think about to get an analog of it is think of a party balloon, one of those long balloons. And the differential pressure is very small when you blow up a balloon compared with being in a pressure suit. I don't even know what the differential is in a real party balloon, but it's, I think, less than 1 psi for sure. And with a suit, you're like 4 psi or 4.5 psi. So you got your arm in those balloons, and you try to bend it. Well, if you try to bend one of those party balloons, you got to use a fair amount of force, even just at a party. But when you're inside it and working it like that, if you don't have some kind of joints that are flexible, you're just bending those balloons, and that's really hard work. And that's why the Gemini EVA flights were really pretty poor, and the guys ended up terminating early, sweat running down their eyes, and Whereas I got to fly the first Apollo suit on Apollo 9, and boy, it was just a world of difference. I had no problems whatsoever. We had what are called convolutes, around the joints, so that when you moved, you didn't change. You didn't have to. The reason why bending a balloon is hard is because you change the volume as you bend it. But when the suits were built so that they would pooch out as you bend your elbow and the knees and that kind of thing. So the Apollo suit was a huge improvement over the Gemini suit. And luckily I got to test it, the backpack that made us independent of the spacecraft. Up until my EVA, we had always had an umbilical cord to the spacecraft. For me, all of my life support was on my back, and all I had to the spacecraft was a rope, a tether, to keep me from drifting off if for some unbelievable reason I decided to let go and push away, both, So it was a very successful EVA, except that the night before I had gotten sick and barfed the day before. So we shortened the EVA, and I didn't get to do the whole hour and a half or so, but I was still outside for 45 minutes and got everything done.
And I think you had a moment that most astronauts in space didn't. There was that 5 minutes during your walk where you didn't have anything to do because there was a technical malfunction with the camera or something.
Right. Dave's camera failed to take pictures of me. Jim McDivitt gave him 5 minutes to try and repair the camera, and I figured, this is my 5 minutes.
Yeah.
I'm not going to be thinking about what comes next. I'm going to say, be here now. You know the old book, but that was clearly the message internally to me was, I'm just going to be here as a human being in space. And that led to a lot of unanticipated questions coming in, like, how in the hell did you get here? Why are you here? What's going on? What's not just going on, but what's really going on? And those were big questions, which I didn't try to answer at that point, but over the next 5 years, that was
Yeah.
a real evolution as I worked those questions. And it's like good wine curing,
Yeah.
or whatever.
It feels like that might be a good transition for us to talk about B612, because
Yeah.
that's certainly looking at the big picture of space and what could happen.
Yeah.
And so let's kind of transition into B612, why you started that, and we'll talk about Asteroid Day some too, which is kind
Yeah.
of part of that.
Well, around, let's see, it was 2000. It was I had already, starting in the early 1980s, founded the organization called what is today the Association of Space Explorers. And that's a professional organization of astronauts and cosmonauts from around the world. And so we had existed for quite a while by that time. But as we came into 2000, Franklin Chang Diaz, one of the astronauts who had flown quite a number of missions, actually. Franklin is a physicist, MIT guy, Costa Rican, actually, by citizenship. But Franklin was into fusion energy. And he realized that if you took, you always have leakage in what's called a magnetic bottle. You make a bottle out of magnetic field and trap very, very, very hot gas in it. And Franklin realized that there was always leakage, and he thought, if there's leakage and I can make the leakage all come out one end, we call that a rocket. And so all of a sudden, Franklin sort of conceptually invented an extremely efficient rocket engine that was essentially a fusion reactor. And so Franklin, at our 2000 annual Congress of the Association of Space Explorers, was making a presentation on this, giving us an update on his development work. And at the end of it, somebody, me or somebody else said, Franklin is really being an extremely efficient engine, but what would you use it for? It's very low thrust. What would you use it for? And so Franklin talked about, speeding up getting to Mars, which is a really good challenge. But he also said, well, maybe we could push asteroids around. It was just sort of off the top of his head. And so a few of us were aware that we were discovering asteroids, more and more asteroids. In fact, Gene Shoemaker and not only Gene, but his wife and David Levy, we're discovering more and more asteroids. And so a bunch of us had lunch together, and we sort of said, well, that's an interesting idea, Franklin, and this is a subject that's pretty interesting. So if anybody does anything with it, let's let the other guys know and see what we can do together. So about a year later, Ed Lieu was lecturing at Princeton University, and he took a walk with one of the physicists at the Institute for Advanced Study, and they said, well, we really ought to try to we're discovering more and more asteroids that could actually threaten impacts with the Earth, but nobody's doing anything about it except finding them. But who's thinking about what do you do? And we said, well, let's have a meeting. So Pete and Ed organized a meeting. A whole bunch of us got together at Johnson Space Center, astronauts, scientists, engineers. We had about 20 of us in October of 2001, I think it was. And so we looked at it for about 3 days together, and we asked two questions. One, could anything be done about it physically? Was technology at a point where we could literally do something? And number two, if the answer to that was yes, which it was, which we decided it was, then we said, can we do something about it? How do we do something which brings it about? And the answer to anybody in government is don't make it happen in government, because it's not going to happen, right? And so we decided the thing to do is to form a nonprofit organization that would take on this question of deflecting asteroids, or could asteroids be deflected, and how, and that kind of thing. And then Pete and Ed and I had beer later in Ed's kitchen there in Houston, and we're sitting around figuring, well, what do we name this organization? And Pete said, I remember reading The Little Prince, and I think The Little Prince came from an asteroid that had a name. And we researched that quickly, drinking our beer, and lo and behold, B612 was the name of the astronaut that The Little Prince came from. So we decided to call it the B612 Foundation.
The inspiration of alcohol. Just amazing things.
Well, and Saint Exupery. I mean, you got to give the author a little credit too, right? But that's how it came about.
Okay.
And then for the first 10 years, I had just retired, and so for the first 10 years, I led the organization. And there was no salary. Nobody in the early days, nobody was paid at all. We sort of paid to do the work. And we developed techniques and explored what could and couldn't be done. It was a very interesting time. And that was our early focus, was the deflection question. But then after about 10 years, I ended up turning it over to Ed Liu, who at that point had just left Google. And Ed decided to shift the emphasis more to improving the techniques for finding asteroids. And so Ed sort of shifted the basic focus. And that's the focus that still exists today in B612.
Yeah.
But now the demonstration of the deflection concepts of kinetic impact, like the DART mission and all, have been at least the early demonstrations.
Yeah.
Fundamental validation of the technology, but not really the operational techniques. That's still to go.
In the early days, was your focus on kinetic impacts or the slow, push with the fusion rocket, or was it a bit of both?
Well,
Which seemed like it was more promising.
Well, the first thing we looked at, and what you think of naturally is, well, you put a rocket, implant a rocket in the surface, and when it's pointed in the right direction, you can rotate the asteroid, point it in the right direction, and fire the rocket. Well, we learned very rapidly that that was absolute lack of understanding. These asteroids tend to be extremely porous. I mean, their bulk density is less than the density of water in many cases. So
you can't really push on a rubble pile.
Yeah, and they became a lot of the smaller, especially medium-sized ones, sort of become what are called rubble piles. They're just loosely agglomerated material held together by mutual gravity. And they have some integrity, but it's always been a question, how much, when they've been together like that for a long while, to what extent do you develop either static forces or some kind of adhesive forces internal to the thing compared with just being lightly held together? And it turns out that the gravitational forces are probably the most important forces. They're pretty lightly held together. And when we went recently out to one and put a sampler down into it, it hit the surface with a fair amount of velocity, and they expected it to sort of bounce off, and grab a bunch of samples. Well, the thing went down almost a meter into the surface, totally unexpected, and overfilled the capacity of the collector. It was interesting.
That's why we do the tests.
That's why you do tests, right?
Yeah.
Well, we rapidly found out you're not going to attach anything to this. It's like attaching something to powder snow, if you want to sort of metaphor of a thing. Well, you can't attach anything. So then the idea of actually having a rocket on the surface and pushing an asteroid was immediately, we gave up on that one.
Yeah.
And the next obvious thing is, well, if you run into it, you're going to transmit momentum to the asteroid, and it's going along minding its business like you maybe on the freeway, and some joker behind you comes in 20 miles an hour faster, and
That never happens.
it never happens to you. Huh? Well, it's happened to me.
Never here in Arizona.
But if you run into an asteroid with a spacecraft going 5,000 miles an hour or something like that, you can change the momentum of the asteroid slightly, And that's exactly what you do when you want to deflect an asteroid. You don't try to change its direction. You change its speed so that it goes into a slightly bigger or a slightly smaller orbit than it was in. And that takes it a little bit longer to go around or a little bit faster it goes around. And that means that it doesn't rendezvous at the right time. The Earth goes through the intersection of the two orbits before the asteroid gets there, or the asteroid goes through the intersection before the Earth gets into the intersection. And that's how you miss each other. That's how we make the asteroid miss the Earth.
It sounds like it goes back to the Apollo days.
Hey, it's a rendezvous, except except you don't stop when you get there, right? Yeah.
As long as you've got the calculations for the orbit right, you don't want to push it into the Earth's.
Well, yeah, but if it's going to hit the Earth, you could make it. Technically, you could make it move either direction, and if you look at the locus of potential impact points, they form a line. It's literally the intersection of the asteroid's orbit with the surface of the Earth. And that makes a line all the way across the Earth. And if it's going to hit the Earth, it'll hit somewhere along that line. But if you imagine that it's going to hit, just take a hypothetical, it's going to hit in the middle of the line naturally. Now, when you make it go faster or slower, you make it either, the impact point either shifts to the right, if you're looking at the Earth here, or to the left. So either ahead of the Earth or behind the Earth. Well, the people who live over here, like Portugal and Spain and, Czechoslovakia or something, are over here, and the United States is over here in the middle of the Atlantic it's going to hit. Well, these guys say, make it go that way. This guy over here says, make it go that way to miss the Earth, right? So that is where we came to understand that the really challenging thing about defending the Earth from an asteroid impact is not the technical, although that's challenging, but the geopolitical decision. Who makes that decision? Who decides which way you deflect it? And what about the people who are put, at least temporarily, in danger as you're moving the impact point through their backyard and off the Earth in that direction or in that direction? So all of a sudden we realized a geopolitical challenge, and I got the Association of Space Explorers, who are a bunch of astronauts and cosmonauts from all kinds of countries, 30-some countries now, to take this on, and we are the organization that took that into the United Nations, and now there are existing United Nations entities that are working these issues. So this is an existential threat to life and the evolution of life in our little corner of the universe. It's a good existential threat in the sense that it's largely a technical problem, but there are other existential threats to our survival, but that's one which we could take on. And so, interestingly, B612 Foundation and the Association of Space Explorers, two organizations I helped found, have taken this on as our contribution to the future of life, really.
And part of the goal of B612 is building awareness about the opportunities as well as the challenges.
Right. Because of the geopolitical challenge, we realized, probably in 2012 or something like that, we can't really expect politicians to make rational choices unless people understand and support them, and even demand that they do make those rational choices. So there's a lot of conflicting self-interest, as you can imagine, in how an asteroid is deflected. So we thought, okay, look, the general public has an intuitive feeling for hurricanes or tornadoes or floods, but the public has no understanding of the existential threat of an asteroid impact. Everybody hears that the dinosaurs got wiped out, right? Yeah, okay, so it's an existential threat, but it's not very real, and there's no intuitive understanding of it. So we decided, hey, we need to start something which would really be dedicated to informing especially young people, about what asteroids are and the good and bad of asteroids. And by the way, it's very interesting. Asteroids both open up the future in terms of resources that we can use in space to move further out into space. And that is a very valuable and important thing. But they also, the bad news, the other side of the coin, is that once in a while they hit the Earth and they wipe out a lot of people, or can. So there's the good news and bad news of asteroids. So Ed Lu and the B612 Foundation have now emphasized both the work that we're doing and being able to discover asteroids being both a positive and a negative challenge that we're dealing with. And that's been a really interesting phenomenon. We're very much, what we're doing is very much tied to the future evolution of life on our little planet.
You mentioned a lot of the technical work you did. I know there have been simulations, places like the Aerospace Corporation will, get involved in even the geopolitical bits. But I like what you said about getting the public involved too, getting them to hold their politicians accountable. It's maybe the best way that the public can get involved, other than just the scientific knowledge and that sort of thing. And that's largely, I imagine, what Asteroid Day is about.
It is. Asteroid Day is, we try to balance both the good news about asteroids and the bad news about asteroids. It's not really bad news, it's a challenge. I mean, the opportunity and the challenge, as it were. But young people are the receptacles for us. I mean, they're all excited about space anyway, almost by nature. I and even my sons and others, we're probably going to be gone by the time that a large enough one to really make a big difference poses a serious threat. And I think we're going to get hit a few times, frankly, hopefully by smaller ones, which are far and away the most numerous, and also in the ocean, which is far and away the biggest part of the Earth's surface. But I think we'll have that kind of a wake-up call periodically, and I have faith that what we're doing now will, in the long run, pay off. We'll be long gone, and nobody will remember what this is all about, or the Schweickart Prize, or B612, or whatever. But
But it's an important thing that the next generation, you set it up for the next generation to continue, and you've done that with the Rusty Schweickart Prize.
Yeah, my family, Danica, who heads the B612 Foundation, years ago when I kind of turned it over to Ed Lu, wanted to have a dinner, a sort of a roast kind of dinner for me. And I said, and combine it as a fundraiser. And I said, I don't like that idea. And so about 10 years later, my wife and Danica and my kids came up with this idea. Let's have a legacy prize, okay, a Schweickart Prize. And so we're giving out annually a $10,000 award to a graduate level student or immediate postdoc student from anywhere in the world who comes up with a good or imaginative idea or concept or project, which if implemented, they don't have to implement it, but if they come up with a concept, which if implemented would make a major difference in the ability of us to protect life on the Earth from asteroid impacts, and they get a $10,000 award.
So how many years have you done that so far?
Well, sort of by default, I was the first award winner of the prize. But so if you count that as year one, we're now in year three. And the award that we're about to give out this year is the third of the awards.
Yeah. Well, we have just a couple minutes left, but I'd love to bring your sons in to just say a couple words because they're really involved with this.
Yeah, absolutely.
You guys want to come over and take our spot for a minute?
Yeah.
Okay, if we're good to go. I'm Randy Schweickart.
And I'm Rusty Schweickart. Not Junior, Rusty B.
And we're the twin sons of Rusty Schweickart. And as Rusty was mentioning, we are part of the founding members of the Schweickart Prize. We were approached by Danica and Nancy Ramsey, Rusty's wife, about participating in the funding of the program. And we're very happy to be co-founders. We thought it was a great idea. Then found out a little bit later how much involved we would actually be in the Schweickart Prize as well. We, as the co-chairs of the program, we help guide the program itself, the selection process, and of course, huge support from the B612 Foundation in executing the selection of the winner. I think the key characteristics of the Schweickart Prize, one, as Dad mentioned, is to involve potential of youth in the next generation, if you will, of protecting the Earth in the planetary defense field. And this was an excellent opportunity to be able to reach out to a broad community, world community. That's what's another important part about this, is that it's international, completely international. And as you find out, asteroids in space is, of course, it excites the entire globe. So with our first start, we had a smaller network to be able to reach out to folks, and now it's gotten larger and larger. And the other aspect that we've looked for is we've tried to expand what types of projects and proposals would be submitted for the Schweickart Prize. And this year especially became extremely challenging because we had some technical proposals, we had some policy proposals, we had some proposals from about communication. So it became a really challenging selection process because we had some very, very good proposals that we had to choose from these different areas. Rusty, you want to talk about?
I just wanted to say, well, of course, we will announce the winner of this year's prize on Asteroid Day on Monday. But the point was that I want to make is that there are 4 members of that team, and they're all from various countries. So it's really an international process, an international award. So it's really neat to see how many people from around the world are participating.
And I think it's a good example that any effort to look at planetary defense has to be an international effort where we're all working together to make it work. So that reinforces that idea, I think.
Yeah, and that actually is part of the award this year is awarded to a group that is doing something that is an international process.
Well, that's great. Well, Rusty, we could talk to you all day. We really appreciate you taking the time, and not just the time to be here, but all the time you spent inspiring people about space and about our place in the universe, and to just look out and wonder. That's something at Lowell Observatory we try to inspire, is to just take a moment, look out and think about your place in the universe, and you so well capture that. And I've been doing it for a long time.
Yeah, it's, frankly, we, the local form of life here in the universe, here on planet Earth, were literally born, or at least conceived, in the Big Bang. I mean, that's the thing that we need to realize. This has been a process of 14 billion years, at least for us, but this is probably happening all through the universe. And we are, in a sense, our own agents, doulas, if you will, at our own birth, out of Earth, Mother Earth, into the larger cosmos. We are historically, in a historical sense, at this moment in time, being born into the larger universe out of Mother Earth. And we have responsibility to the future. And I think that's the image of the big picture of what we are all involved in. And I think whether we will be stillborn in this process or whether we'll make it through that very narrow channel of birth is in some sense up to us and up to the understanding that we all have of what we really are here is life in the universe, and we're about to expand into it if we're able. So
That's a really inspiring metaphor, and also a call to action, I think.
yeah, cosmic birth was a name I've sort of used to describe it. It's a surprisingly valid metaphor.
Well, I think that's a really good thought to end on, and something to keep us all thinking. So Rusty Schweickart, thanks so much for joining us. Dr. Kyler Keene.
Thank you.
And thank everybody for joining our podcast. We'll see you next time on Star Stuff.
This podcast was made possible by our members and donors. If you enjoyed this episode and want to support our nonprofit in making more digital education like this available, go to lowell.edu/donate. Thanks for listening.